So we are starting Module 7, Sampling Distributions. In Module 7, this is going to be 3 different sections. Section 1 is what is a sampling distribution. 2 would be sample proportions, and 3 sample means. So let's start in 7.1. Our learning objectives are the following. Distinguish between a parameter and a statistic. Define the sampling distribution. Distinguish between population distribution, sampling distribution, and the distribution of a sample. Determine whether a statistic is an unbiased estimator of a population parameter, and describe the relationship between sample size and the variability of an estimator. All right, so what does it mean to be a sample versus a population? So this little down here, you could think a sample is kind of like a subset of the whole population. So you take part of the population and you can do a sample, you collect the data, and you see if you can make an inference about the population. Because sometimes it's impossible to get like the whole population sampled. All right, so as we begin to use sample data to draw conclusions about a wider population, we must be clear about whether a number describes a sample or a population. So you have to be very, very clear about that, and there's different variables for each. So a parameter describes a population. I remember P and P, and a statistic describes the sample, so S and S. So if you're talking about a statistic, you're talking about a characteristic of a sample. If you're talking about a parameter, you're talking about a characteristic of a population. So P and P and S and S. All right, so mu is the Greek letter for a population mean, and X bar is the symbol for a sample mean. Whenever you're dealing with populations, these are always going to be Greek letters. And you could think it's like a populi, however you spell that, for the Greek word populi. Okay, but you're always going to have Greek letters going on. So mu, when you talk about mu, yes, that is a mean, but more importantly, it's a population mean. And X bar is the sample mean. When you're dealing with a sample proportion, you're going to use P hat. And if you're dealing with the proportion for the whole population, you're going to have P. So if you take lots and lots and lots of samples in the population, you could make a better inference, basically. Okay, so you can be more and more accurate of what the whole population parameter would be by taking a lot of sample statistics. Okay, example, let's identify the population parameter, the sample, and the statistics in each of the following settings. The Gallup poll asked a random sample of 515 U.S. adults whether or not they believe in ghosts. Of the respondents, 160 said yes. So what are you finding here? Is this from a sample or is this from a population? So this is from a sample. And here you're saying that you're going to do 160 out of 515 that said yes. So you're taking a proportion, and since it's from a sample, it's going to be P hat. Okay, B. During the winter months, the temperature outside the DeRosa's cabin in Colorado, I really don't have a cabin, but can stay well below freezing for weeks at a time. To prevent the pipes from freezing, Ms. DeRose sets the thermostat at 50 degrees Fahrenheit. She wants to know how low the temperature actually gets in the cabin. A digital thermostat records the indoor temperature at 20 randomly chosen times during the day. The minimum reading is 38 degrees Fahrenheit. So what are we doing? Well, the population here would be the entire winter months. So all the time, constantly. And the sample are those 20 readings. The population minimum, we don't have a symbol for that, okay? And we don't know what it's going to be. However, I know the sample minimum, and there's no symbol for that, but I know the sample minimum is 38 degrees. So that is a statistic of being 38 degrees. Okay, C, a random sample of 1,000 people who signed a card saying they intended to quit smoking were contacted 9 months later. It turned out that 210, which is 21% of the sampled individuals, had not smoked over the past month. All right, so let's see, what would your population be? So your population would be all people who signed the petition or who signed whatever it was, the contract. Your sample, in this case, are the 1,000 people who signed. We do not know the population proportion P. However, we do know the sample proportion P hat is 21%, or you could put 21 out of 1,000. All right, so an AP exam common error. On the AP exam, many students will lose credit because you can't make the distinction between parameters and statistics. So for example, in a significance test, which we will get to later, when you write in the hypothesis, if you just like say the mean and you don't say if it's a population mean or a sample mean, you're going to lose credit. So it's important to know what you're dealing with. So are you dealing with the population mean, which is also called the true mean? If you just say mean, you will not get full credit. Same thing with me as I grade. I need to have that clarification. All right, so each boldface underlined number in questions 1 and 2 is the value of either a parameter or a statistic. In each case, state which it is and use appropriate notation to describe the number. So I'm going to let you read through those, see if you can write it down. You can pause for a second, and then let's see how you do. All right, so hopefully you have unpaused now. If not, keep pausing. The 20 right here is a population mean. Okay, so this is a parameter. And the population mean symbol is mu equals 20. Remember, Greek cows say mu. Okay, and then this 19.6, this is the sample mean. So this is a statistic. And the sample mean is x bar would equal 19.6. Okay, on the next one. Right here, this 8%, this was on one flight out of many. So this is a parameter. This would be the population proportion. And that is P equals 0.08, or you could say equals 8%. 10% is the, sorry, erase what I just said. That's not the population. That was one flight. Hopefully some of you are like, what, Mr. Rose? All right, so this was a sample proportion. So sample proportion is going to be P hat equals 0.08, and that means it is a statistic. Is that better? All right. Now, the 10%, this is saying for all flights is that 10%. So this is the population proportion. This is a parameter. And we use P equals 0.10 or P equals 10%. All right, much better. Sorry about that. Okay. So just a little activity if you want to kind of think about this. Let's say that you are here with me right now and I have 200 colored chips, 100 having the same color, red. Okay. The parameter is the actual proportion of red chips in the population. So if there were 100 out of the 200, then this P is going to be what? 1/2. Or you could say 0.5. In this activity, you will investigate sampling variability by taking repeated random samples of size 20 from the population. So let's just think about if you had done this. Okay, so after I mix up the chips thoroughly, each student in the class will take 20 chips and note the sample of the red chips, return the chips, pass it to the next student. And then that student takes 20, gets the proportion of red chips. Again, that's going to be a P hat. That's a sample. And then put them all back in, pass it to the next one. Okay, so we are replacing all the chips for each student. Okay, so then each student should record the P hat value in a chart on the board and plot this value on a class dot plot or histogram and label the graph scale from 0.10 to 0.90 with tick marks placed 0.05 units apart. So we're not going to actually do this activity, but we're going to reference it. If this had happened, let's say that I collected that data and it looked something like this. Okay? So one student got a proportion of 0.2, one student got a proportion of 0.3, two students got a proportion of 0.35, etc. All right, so in this activity, we took a handful of different samples of 20 chips. There are many possible samples that we could do of size 20 from the population of 200. If we took every one of those possible samples, calculated the sample proportion for each, and graphed all of the values, we'd have a sampling distribution. Okay? Every possible sample and graphed. That's a sampling distribution. So here you can say a sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples. And it has to be the same size. So that's important too. They have to be that same size, all possible samples. So it's really hard to take all possible samples of size n and to see what's actually going on to get the sampling distribution. So we're going to use a simulation to imitate the process of taking many samples. All right, so population distribution versus a sampling distribution. There are three distinct distributions involved when you sample repeatedly and measure a variable of interest. So a population distribution gives the values of the variable for all individuals in the population. The distribution of a sample, so that's different than a sampling distribution, I know, crazy, so get those vocab terms down. The distribution of a sample data shows the values of the variable for all individuals in the sample, and the sampling distribution shows the statistic values from all the possible samples of the sample size from a population. Are you like, what? That's okay, hang in there. It's going to make a little bit more sense. So let's look at this. Ooh, why are those green lines still there? That is odd. Okay. So here, I can see I could take my population distribution. Let's say that 100 were the red chips and the other 100 were blue. Okay? So there's my population distribution. Then I went and I got lots of different samples. So this is all distributions of sample data. And this is what happened for one student. They got 8 red, 12 blue. So there was their sample proportion. This student got 9 blue, 11 red. So here's theirs. This student got 7 blue, 13 red. There's their sample proportion. Putting all those possible samples together, so after doing it over and over and over and over, you get the sampling distribution of everything that could happen. Hopefully that helps clear it up a little bit. Okay, so common error again is that terminology. You have to say those vocab words correctly. If you don't say sample distribution when you meant to say sampling distribution, you're going to lose credit. So make sure you know how to use those appropriately. So here, let's look at this first example. All right, Mars Incorporated says that the mix of colors in its M&M's candies is 24% blue, 20% orange, 16% green, 14% yellow, 13% red, and 13% brown. And I think that there's other colors now, aren't there, in M&M's? Maybe not. No, because blue's the new one, right? Okay, anyway, assume that the company's claim is true. We want to examine the proportion of orange M&Ms and repeated samples of 50 candies. Graph the population distribution. So the population distribution is just putting the blue was 18%. Is that right? Or what did it say the blue was? 20% orange. Why is that off? I think I maybe wrote those down right. Well, let's say that the blue was 18%, the brown was 8%. Yeah, I really got those off. I did not write those correctly. Okay, but let's just say that, so blue was 18%, or maybe I just didn't get my graph right. Do they add up to 100? Grr. Let me pause you really quick. Okay, sorry about that. This was for part 3. The third question I was asking about these 3 graphs. All right, so if I move on, if I look at this slide, there is my population. So it was, as it said before, 24% were blue, 20% orange. This is looking much better. And you can see 16% green, 14% yellow, etc. So there's my population distribution. Yay! All right, so then it also asked me to identify the individual, the variable, and the parameter of interest. So here I can see the individuals are the M&M's milk chocolate candies. The variable is going to be the color, and the parameter of interest is that proportion of orange M&M's. So that's what it asked me for. Okay? So we want to examine the proportion of orange M&Ms. So that's why it's the parameter of interest. So 2, imagine taking an SRS of 50 M&Ms, make a graph showing the possible distribution of the sample data, and give the value of the appropriate statistic for the sample. All right, so that may take you some time. But here you can see that for this sample, there's going to be 11 orange M&Ms that I did. And this was my sample of what happened. You may have something different. It just was a possible distribution for a sample. So they just have to add up to 50. And again, like, so 50, 24% of 50 would be 12. So you couldn't have any more than 12 blue. All right. Which of the graphs? Well, I guess actually you could go get an M&M and it could be off, right? It doesn't have to be what Mars says. All right. So maybe go buy a bag of M&Ms and treat yourself while you're doing this and see what actually happens. Number 3, if you were in my classroom, I'd give you M&Ms, but like if I saw you face to face. So if you want M&Ms, just come find me. All right. Number 3, which of the graphs of the graphs that follow could be the appropriate sampling distribution of the statistic, and explain your choice. So I'll let you look through those. All right, hopefully you circled or you wrote down that it couldn't be A, that would look more like the population, okay? So here, if I wanted to find the sampling distribution, it is going to be this middle one. So here I have it written down so I can read why you kind of can see it. So the middle graph is the approximate sampling distribution of p-hat. The statistic measures the the proportion of oranges in samples of M&M's milk chocolate candies. Assuming that the company's correct, 20% of the M&M's are orange, so the center should be at about 20%. So let's look here. Is the center about 20%? It's going to be what they've claimed it to be. So if the claim they said was 0.20, then we should have a center around there, unless they're just really lying to us, which I don't think they are. Okay? Okay. So the fact that statistics from random samples have definite sampling distributions allow us to answer the question, how trustworthy is a statistic as an estimator of the parameter? To get a complete answer, we consider the center, the spread, and the shape. So we're going to talk about biased and unbiased estimators if we deal with center. So if I had that chips example, we collected many samples of size 20 and calculated the sample proportion of red chips. So how well does this sample proportion estimate the true proportion of red chips? So we can see that the center here was close to what they had of 0.5. And in fact, if you took all the samples of size 20, you'd find that you get exactly 0.5. So this tells us that this would be an unbiased estimator. All right, what about the spread? Well, you want something that is low variability, so you do not want it very spread out. So to get a trustworthy estimate of an unknown population parameter, start by using a statistic that's an unbiased estimator. This ensures you won't tend to overestimate or underestimate. Larger samples will have a clear advantage over smaller samples. They are much more likely to produce an estimate close to the true value. Okay, so the larger the sample, the less variability. So here the variability of a statistic is described by the spread of its sampling distribution. This spread is determined primarily by the size of the random sample. Larger samples give smaller spread. The spread of the sampling distribution does not depend upon the size of the population, as long as the population is at least 10 times larger than the sample. That's what we've talked about to be independent, that 10 times larger than the sample. So 10n, the population has to be at least that. Okay, so 10 times n, the number of your sample, has to be less than or equal to the population. Okay. The histogram on the left shows the intervals in minutes between eruptions of Old Faithful, the geyser, for all 220 recorded eruptions during a particular month. That's a lot for a month. All right, for this population, the median is 75 minutes. Using software, 500 SRSs of size 10 from the population are taken. I think that should just be SRS, like SRSs, so simple random samples. Okay, anyway. Then the 500 values of the sample median are displayed in the histogram to the right. The mean of the 500 sample median values is 73.5. So the mean of the medians is 73.5. So is the sample median an unbiased estimator of the population median, and justify your answer? So we had from 75 to 73.5 5. That's a pretty large gap, so I would say that it is not unbiased. It doesn't appear to be unbiased. Now, if you feel like that's not a large gap, you could say that it would be, like, if you think that that is a large gap, you would say it's biased. But since it's fairly close, sorry about that, it would be unbiased because it is fairly close together. I think that that's a pretty good indicator. Okay, so that would be an unbiased. If this one came out to be like 50, that would definitely be biased. That would be bad. All right, suppose we had taken samples of size 20 instead of size 10. Would the spread of the sampling distribution be larger, smaller, or about the same? And tell me why. All right, it would definitely be smaller. Larger samples decrease the variability. And 3, describe the shape of the sampling distribution. Explain what this means in terms of overestimating the population median. So here I can see that this is definitely going to be what? Skewed left. So this means that, in general, overestimates of the population median will be greater. Okay. Underestimates of the population median will be greater than the overestimates. And here you can see. So if I'm skewed left, that median gets pulled. So I'm probably going to underestimate more than the overestimates. I'm going to pause really quick. I will be right back. Okay, sorry about that. So, when describing sampling distribution, we want to talk about bias, variability, and the shape going on. So this I love. You can kind of think about it like with the target. So here, you're really far away from the target, so you're going to have a high bias because you're really far away. However, since everything's all close together, you will really like, you kept getting the same thing over and over. That's good because that's a low variability. You just got to somehow get your aim to go a little bit closer. So you have a high bias but low variability. Here, you are hitting the target closer and closer, so you're really close to the target. However, they're all over the place, so this one's going to have a low bias because you're close to that target, but it's going to have a high variability. All right, this one's the worst. You have high bias because you are away from the target, and since you are all over the place, you also have a high variability. So that is the worst to have. The best to have would be low bias, they're all in here in the target, and low variability, they're all close together. So this one would be the best. So bias means that our aim is off and we are consistently miss the bullseye. Okay? It's a good way to kind of think about it. And variability means that repeated high variability means that you're scattered. Okay? Low variability would be all together. Okay, so the lesson about center and spread is clear. Given a choice of statistics to estimate an unknown parameter, choose one with no or low bias and low variability. All right, so this is just an activity. Again, we're just going to kind of talk about it. We're actually not going to do it on the discussion board, but it is just kind of cool to think about. During World War II, the Allies captured several German tanks. Each tank had a serial number on it. Allied commanders wanted to know how many tanks the Germans actually had so that they could allocate their forces appropriately. They sent the serial numbers of the captured tanks to a group of mathematicians in Washington, D.C. and asked for an estimate of the total number of German tanks. So this is real, okay? This is actually what happened, and I would love to have been a mathematician there. I think, well, actually I wouldn't. I don't know. I couldn't do the war thing, but I love patterns and findings. So in this activity, you and your teammates will, or just you in this case, or you could talk it over with people around you that you know are taking this class. So play the role of the mathematicians, okay? And we actually aren't going to have the extra credit or anything here, but you're going to play the role. So let's say that I had tags and I numbered them 1 through some unknown n, just like the number of German tanks. Okay, so there's at least one tank and we don't know how many they go up to. And so that represents the German tanks. And I place them all in a bag. And you guys can be in teams or you can just try this by yourself. But the teacher, I'm going to mix up the tags really well. And I ask 4 students to draw one tag from the bag. Okay? Each selected tag represents a serial number of a captured German tank. All 4 numbers should be written on the board for everyone to see. And then we're going to return the tags to the bag. Okay, so each team will have 15 minutes to come up with a statistical formula for estimating the total number of tanks. So I'll just let you think about what your formula would be. And I'm going to tell you what those numbers are going to be. I'm going to use my random integer function here. And I know what n is, you do not. So the first one I got was 184 and the next one I'm gonna get is 190. That's crazy. Pretty close together. The next one I get was 110 73. I'm gonna go ahead and give you one more maybe. 291. Let's just say I gave you even 5. So those, you got 5 captured. I want you to think about how you could estimate what's going on with how many there actually are. So you don't know, but you've uncoded all the serial numbers and you figured out that one of them is the 73rd, one of them is the 110th, one is the 184th, one is the 190th, and one is the 291th tank. Okay? So, see if you can think about that. You could pause me. You could, yeah, because I'm going to show you some ways that some people have thought about it. Okay, so you want to try to think, what did you think n was going to be? Okay, how many tanks are actually out there? That's your goal. And here's a little link if you want to go to it that actually talks about it. I'll go ahead and click on it. Oops, here, let me set this down so you can see. But German tank problem, so it's an actual thing that happened. You can go learn more about it if you want. Oh, what happened? German tanks, here we were. Resume slideshow. Okay. So this was one thing that actually happened, that they found, the statisticians or the mathematicians said they estimated 169 and the intelligence people estimated 1,000 and there were actually 122. So here in June of 41, the mathematicians said 244. The intelligence estimated 1,550, and the actual number was 271, so they were pretty close. And look at this in 1942. Isn't that crazy? Like, crazy! Math is awesome. Alright, so here were some ways you could think about it. Maybe. Yeah, here. So here, this was the max min. Here was the mean, I think, plus 2 times the standard deviations. Here they did twice the mean. Here they did 2 times the median. And I don't remember what partition was. I'd have to look that up for you again. But this is what people thought about, some different ways. And the actual number here, I think it was, I just wrote it down, I just lost it. It was close to 350. It was like 347 or something. How did you do? Did you come close to it? what that actual one was. So here, the max-min was the maximum plus the minimum. The mean plus 2 standard deviations, twice the mean, twice the median. Oh, here, did it say what the last one was? Oh, yeah. The partition, the dot plot to show the results of taking 250 SRSs of 4 tanks, recording the value of the 5 statistics of each sample. Okay. Oh, there are 342. That's what it was. I was just like, I just wrote it down when I did it in my calculator and then I cleared it. All right. So there are 342 tanks total. So how did you do? Hopefully you did okay. The one that the mathematicians did was 5/4 times the maximum. Isn't that crazy? All of that work, and that's what they decided. So they felt like that was the most unbiased estimator, was to do the 5/4 maximum. So what was the most biased? Let's look over here. Gosh, the most biased looked like it'd be twice the median. Okay, the lowest variability would be the partition, but it's still spread out, and it's heavy, so it's going to be skewed towards the left. But try that 5/4 maximum and see what happens with the data that we had. That'd be pretty cool to find out. Okay, so in summary for 7.1, this is what we talked about. And we're going to start 7.2 next.